shall return.
On April the 1st, 2026, 4 human beings climbed into a capsule sitting on top of 3.5 million pounds of rocket fuel and were launched further from Earth than any person has traveled in over half a century. The rocket beneath them stood 322 feet tall. In 8 minutes, it generated 8.8 million pounds of thrust, 17% more than the Saturn V that sent men to the moon in 1969. And it sent them on a 10-day journey around the moon and back. But here's the part that most people don't know. This mission took 20 years and $93 billion to reach that moment. It was supposed to launch in 2016. It didn't fly until 2026. The heat shield on the capsule showed unexpected damage during its only uncrewed test flight, and some of the engineers who examined it formally objected to putting a crew on board. They flew anyway. This is the story of Artemis II, the most complex, most expensive, and most controversial space mission of the 21st century. And what they attempted is something that, 54 years ago, required nothing more than slide rules, hand-drawn calculations, and a computer with 4 kilobytes of memory. So why is going back so much harder than going in the first place? To understand Artemis II, you need to understand the machine that makes it possible. The Space Launch System, SLS, is the most powerful operational rocket ever built. It stands taller than the Statue of Liberty. Its core stage alone is 212 feet tall and holds over 725,000 gallons of supercooled liquid hydrogen and liquid oxygen. When those propellants mix and ignite inside the 4 RS-25 engines at the base, they produce approximately 2 million pounds of thrust. But that's not even the main event. Strapped to either side of the core stage are 2 solid rocket boosters, each one 177 feet tall, 12 feet in diameter, and weighing 1.6 million pounds. Each one produces 3.6 million pounds of thrust for 126 seconds. Together, those 2 boosters provide over 75% of the total thrust at launch. The RS-25 engines handle the rest. Combined, the system generates 8.8 million pounds of force, enough to accelerate 3.5 million pounds of hardware from a dead stop to 3,100 miles per hour in the first 2 minutes. And that raises an obvious question. If this rocket is 17% more powerful than the Saturn V, and we have 60 years of additional engineering knowledge, why did it take 20 years and nearly $100 billion to build? The answer is uncomfortable, and it starts with a heat shield. In November 2022, NASA launched Artemis I, the uncrewed test flight of this exact rocket and capsule. The mission was technically successful. Orion flew to the moon, orbited, came back, and splashed down in the Pacific Ocean. But when engineers recovered the capsule and examined the heat shield, they found something they didn't expect. Sections of the AV coat ablative material, the coating designed to burn away in a controlled manner during re-entry at 25,000 miles per hour, had eroded unevenly. Chunks were missing. The char pattern didn't match any of the pre-flight models. The temperatures inside the capsule stayed within safe limits. But the fact that the heat shield behaved unpredictably created a problem that would consume NASA for the next 3 years. See, a heat shield isn't like a damaged wing or a faulty engine. You can't observe it failing in real time. If it fails during re-entry, the crew is dead before anyone on the ground knows there's a problem. There is no abort option at 25,000 miles per hour, no escape system, no backup plan. The heat shield either works or it doesn't. NASA's response was extensive. They ran additional tests. They built computer simulations modeling scenarios far worse than what Artemis I experienced. They concluded that even under conditions exceeding the expected re-entry profile, the underlying structure of Orion would remain intact and protect the crew. Some of the engineers who had originally raised concerns reviewed the new data and agreed the analysis was sufficient. Others did not. Some engineers continued to formally object to flying a crew on a capsule whose heat shield had behaved in ways they could not fully explain. Their concerns were noted. The mission was approved anyway. That tension between institutional momentum and engineering caution is one of the defining stories of Artemis, and it echoes a pattern that has haunted NASA before. Challenger in 1986 and Columbia in 2003 were both disasters in which engineers raised concerns that were overridden by schedule pressure. NASA insists this situation is different. The data supports proceeding, the margins are sufficient, but the parallel is impossible to ignore, and the people in that capsule know it. Now, let's talk about the people in that capsule. There are 4 of them. Commander Reed Wiseman is a 27-year Navy veteran, a fighter pilot who has flown F-18s and served as a flight engineer on the International Space Station. Pilot Victor Glover is a test pilot who flew F/A-18 Hornets and Super Hornets before becoming one of the first crew members to launch on a SpaceX Crew Dragon. Mission specialist Christina Koch holds the record for the longest single spaceflight by a woman, 328 days aboard the ISS. And mission specialist Jeremy Hansen is a Canadian Space Agency astronaut, a former CF-18 fighter pilot, and, if this mission succeeds, the first non-American to travel beyond low Earth orbit. Let me say that again. In the entire history of space exploration, every single human being who has left low Earth orbit has been an American citizen. Every Apollo astronaut, every person who has traveled beyond a few hundred miles above our planet, all of them American. Jeremy Hansen will be the first person from another country to break that barrier. Victor Glover will be the first person of color. Christina Koch will be the first woman. And if Orion travels beyond 248,655 miles from Earth, which current projections suggest it will, this crew will break the distance record set by Apollo 13 in 1970. The crew will fly further from home than any human being has ever been. So what does the mission actually look like? At launch, the 2 solid boosters and 4 RS-25 engines fire simultaneously. For the first 2 minutes, the boosters do the heavy lifting, generating over 7 million pounds of thrust and accelerating the stack to 3,000 miles per hour. At an altitude of 30 miles, the boosters separate and fall away. The core stage continues burning for another 6 minutes, pushing Orion into a highly elliptical orbit roughly 1,200 miles above Earth, nearly 5 times higher than the International Space Station. Then, something interesting happens. The crew spends the next 23 hours in Earth orbit, circling the planet twice, running systems checks, and preparing for the maneuver that will send them to the moon. During this time, Orion is still attached to the upper stage, the interim cryogenic propulsion stage, which will fire its engine to accelerate the capsule to 24,500 miles per hour. That's the speed required for translunar injection, the trajectory that breaks free of Earth orbit and sends them toward the moon. Once the burn is complete, Orion separates from the upper stage. From this point, the crew is alone. 4 people in a capsule roughly the size of a large SUV, heading toward the moon at over 20,000 miles per hour with no engines capable of turning them around. They are committed. The outbound journey takes approximately 4 days. On day 5, the crew reaches the moon. Orion will fly to within approximately 6,000 miles of the lunar surface, close enough that the moon fills most of the window, appearing roughly the size of a basketball held at arm's length. Then the spacecraft swings around the far side, out of contact with Earth for approximately 30 minutes. During that time, the crew will see something no human has seen in person since 1972, the far side of the moon, lit by the sun, with the Earth completely hidden behind it. After the flyby, Orion begins the return journey. The trip home takes another 4 to 5 days, during which the crew continues testing systems and conducting experiments. On day 10, the capsule hits the atmosphere at 25,000 miles per hour, faster than a bullet, faster than any vehicle most people have ever conceived of, and the heat shield must absorb temperatures exceeding 5,000 degrees Fahrenheit. If the AV coat performs as the engineers predict, the capsule will decelerate, deploy its parachutes, and splash down in the Pacific Ocean off the coast of San Diego. If it doesn't, there is no plan B. Now, here's the question that sits underneath all of this. In 1969, NASA sent 12 men to the surface of the moon across 6 successful landing missions. They did it with a computer that had 64 kilobytes of memory and a clock speed of roughly 2 megahertz, less processing power than a modern digital watch. The entire Apollo program cost approximately $257 billion in today's money and ran for 11 years from announcement to final mission. Artemis has cost $93 billion so far, has been in development for over 20 years, and has not yet landed anyone on the moon. Artemis II is a flyby. The crew will loop around the moon and come home. The earliest landing mission, Artemis III, is not expected until 2028 at the earliest. That's 6 years after the uncrewed test flight and 59 years after the first Apollo landing. So what happened? Part of the answer is that Apollo operated under conditions no modern program could replicate. A limitless budget driven by Cold War urgency, engineers who accepted risk levels that would be career-ending today, astronauts who understood they had roughly a 1 in 4 chance of dying. The Apollo 1 fire killed 3 astronauts on the launch pad, and the program continued within 21 months. That calculus is unthinkable in 2026. But part of the answer is also that Artemis was designed by committee, built by contractors who were paid on cost-plus contracts. meaning the more they spent, the more they earned, and managed through a political system that changed direction with every new administration. The SLS rocket uses engines originally designed for the space shuttle in the 1970s. The solid rocket boosters are literally rebuilt from shuttle-era hardware. NASA was directed by Congress to use this existing technology specifically to preserve jobs in key congressional districts. Engineering decisions were shaped by politics, and the result is a rocket that is undeniably powerful, but took a decade longer and tens of billions more than originally projected. None of that mattered to the 4 people who climbed into that capsule on April the 1st. When the countdown reached 0 and 8.8 million pounds of thrust pressed them into their seats, the engineering debates and budget overruns and political compromises became irrelevant. What mattered was whether the hardware worked, whether the calculations were right, whether the 4,700 miles beyond the moon that the trajectory demands is a distance the capsule and its crew can survive. For the first time in 54 years, human beings have left the neighborhood of Earth and are heading for the moon. 4 of them, in a capsule that weighs about 11 tons, launched on a column of fire that burned hotter than the surface of the sun. And the only thing that will stand between them and the vacuum of space on the way home is a heat shield that didn't behave the way it was supposed to the last time it was tested. Godspeed, Artemis.